Hi, and welcome again to my Physics Online video lecture series. Today's video is going to be, by necessity, more of a long example than much of anything else. What we're doing is kind of putting together the last few videos that I've done on vector resolution or vector addition and putting them into basically terms of taking a vector or a set of vectors that has been given to us in polar coordinates and then adding them together, but using the algebraic method, which is meant for more usually for Cartesian coordinates. So this is really just to kind of walk through the whole long process via an example, which I will try to keep as short as I can. You'll recall that when we discussed the recipe for adding vectors in Cartesian coordinates, that we began with this step of convert all vectors to Cartesian if necessary. Then we talked about adding all the x's to get the resultant x, add all the y's to get the resultant y, and if necessary add all the z's to get the resultant z, and then put it all back together, the resultant being rx, ry, rz, with step 4 being convert back to the original coordinate system. Now in that original video, I basically worked a quick example that involved largely steps 2 and 3. In other words, I gave you an example with a vector that was already in Cartesian coordinates, and you needed to find the resultant vector from adding a few such vectors together, also in Cartesian coordinates. I also, in the other video that I've done on adding vectors for this level of class, I also discussed adding in polar form using the geometric method. So today I kind of want to put those two things together, and we're just going to actually revisit an example from a previous video in which I asked you to use the geometric method. So what's going to change in today's video is instead of using the geometric method, today we're going to use the algebraic method to add these three vectors together. Now we should get the same result or something very close to it as we had before. This will, however, give us the opportunity to use the entire longer recipe. So we've been given three vectors, and the first step in our recipe is to convert all these vectors into the Cartesian. So step 1, convert to Cartesian. And the process of converting to Cartesian, you'll recall, basically involves multiplying r times sine or cosine of theta to get y and x respectively. So if each of these above vectors, we could call it f sub I for individual, is represented by force I, comma, cosine, comma, phi I, or theta I, then we are converting this into Cartesian using that magnitude Fi times the cosine of the angle, comma, Fi times the sine of the angle. So we're basically going to do this several times over. So F1 would be represented by 125 newtons, comma, 30 degrees. This basically means that F1 is 125 newtons and phi 1 is 30 degrees. So this can then be represented by 125 newtons times cosine 30 degrees, comma, 125 newtons times sine of 30 degrees. So you may want your calculator for this. Make sure that you are in the correct mode, specifically degree mode. 125 times the cosine of 30 degrees gives me 108.2. I'll keep the 0.2 for now. 108.25. So I guess I should maybe round it to 0.3. So 108.3 newtons, comma, and then the other one, 125 times the sine of 30 should be 62.5 newtons. All right. Now we need to do that for the other two forces as well. I'm going to pause, do that so that you don't have to watch me putting everything in. You should likewise pause the video here and calculate these yourselves and then compare your answers to the ones that I get. All right, so after plugging into my calculator in the same process that I used here for F2 and F3, these are my vectors as represented in Cartesian coordinates. We're ready now to do step 2. So we got to add the x's, we got to add the y's. Might actually make sense for step 2, adding the component terms. We could just say add like components as a shorthand to kind of like what we did when we first learned how to do addition. Line them up like this vertically and then add all of the results together. So we have 108.3, we have negative 50, so 108.3, negative 50.0, and then the last one was 51.3, so 51.3, comma, 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 chameleon. And then 62.5 and 86.6 and negative 141.0, so minus 141.0. Of course, these are all, every one of these units is in newtons. So if I add up everything over here, I should get a positive, and you could think of these as like positive and positive, 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 negative. So I should get positive 109.6, and then for the other side it comes out to 8.3. So I'll call that 8.3, positive 8.3 newtons. So this was step 2. This right here actually would be to say that the total or net or whatever we want to call it, I guess we label it just as F, would be represented by this number here. So this is actually step 3 on our recipe. Step 4 is converting it back. So step 4, convert to polar. Now, to do step 4, it's actually not a bad idea to draw ourselves a diagram, which we actually did do in the previous video when we added these together, because we, well, drew diagrams in order to add them anyway. The resulting vector is in this quadrant. So this side right here has 8.3 newtons. This side right here is my 109.6 newton side. This would be F, and this would be phi. So knowing that this always makes a right triangle, x and y are always perpendicular to each other for any orthonormal basis system. So this basically has created a right triangle whose sides have these two lengths. So it should be obvious that f squared, the hypotenuse squared, should be the first leg squared plus the second leg squared. And so f squared is 109.6 newtons squared plus 8.3 newtons squared. So if I add those two to each other, that 109.6 squared plus 8.3 squared, I end up getting that f squared is 12,081.05 square newtons. Now I need to take a square root of both sides to get f. So if I take the square root of both sides, I get 109.91. So I'm just going to actually now say it's 109.91 newtons. Really, we can only maybe retain to this digit due to significant figures. So this is approximately 110 newtons. Okay, now we do the angle. Well, tangent of the angle should look like opposite, that would be Fy, over adjacent, that's Fx. Now, because we're in the first quadrant, we don't need to do any further modifications for this. We can just plug the numbers straight into our calculator, and the correct answer should come out the other end. So if I divide these things by each other, I want 8.3 divided by 109.6, and what I end up with is 0.0757299. So that means that phi is the inverse tangent of this, so I use the tan -1 button, and I get 4.33 degrees. 4.33 degrees. So I can write, using this here and using this here, I can write my final answer in polar coordinates, that F can be represented approximately by 110 newtons, comma, 4.3 degrees. So what did we get when we did this before using the geometric method? Let's look at the kind of end result from the geometric method. This was after I converted to a scale. 1 inch is 25 newtons. I added them up using, well, LibreOffice as a drawing program, and then I got the result and measured it. I got 109.75 newtons, comma, 4.25 newtons, and I said at the time that that was probably more significant figures than I ought to have. So if I round this off to 2 significant figures in the nearest whole here, this is approximately 110 newtons, comma, 4.3 degrees. In good agreement with the result that we got at the end of this calculation that I did for today's example. So, that is an example. Is there anything to add to it? Only the warning that you got to pay attention to what quadrants you ended up in. And that's just because not all calculators are created equally. You may have to do a little bit of coordinate quadrant shifting to get the correct angle. So pay attention to your quadrant. I believe I discussed that earlier when talking about just converting coordinate bases, however. So I'm not going to say anything further about that today. So that's it. I hope you learned something from this, and thanks for watching.